welcome to Electrical Circuit Analysis. Throughout this lecture, I'd like to request you to pause this video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. A capacitor is a passive element designed to store energy in its electric field. Besides resistors, capacitors are the most commonly used electrical component that are used extensively in communications, computers, electronics, and power systems. One common example of capacitor application is that they're used in the tuning circuits of radio receivers and as dynamic memory elements in computer systems. So when you're turning the knob of the radio that says different frequencies, 90 megahertz, 91 megahertz, something like that, you're basically changing the value of a variable capacitor. A capacitor basically consists of two conducting plates separated by an insulator or dielectric. So here's an illustration: two conducting metal plates separated by an insulator known as a dielectric, and this dielectric has a certain permittivity, epsilon. So when a voltage source is connected to the capacitor, positive charges are deposited in one of the plates and negative charges are deposited on the other plate of the capacitor. The capacitor is set to store the electric charge, and the amount of charge stored, represented by Q, is directly proportional to the applied voltage. So Q here is proportional to V. So every proportion can be written with the proportionality constant. So Q equals to CV, we can write here, where C is the constant of proportionality. The C here, this constant of proportionality, is known as the capacitance of the capacitor, and the unit of capacitance is farad. So another point to note is that when we apply a certain amount of voltage V, the charge that gets stored in the two plates of the capacitor are equal. This is Q here, this is also Q. But they're opposite charges. One plate has positive charge, another plate has negative charge. And the amount of charge that is going to get stored in the capacitor depends on the voltage applied and the capacitance of the capacitor. So the higher the voltage or the capacitance, the higher the charge that are deposited on the capacitor plates. Capacitance is the ratio of the change of the charge on one plate of a capacitor to the voltage difference between the two plates. So 1 farad is basically 1 coulomb per volt. So even though the amount of charge deposited in the plates depends on the voltage, the capacitance itself does not depend on the charge or voltage. It depends on the physical dimension of the capacitor. So however high or low voltage we applied across the capacitor plates, the capacitance doesn't change, but the Q changes. The capacitor, for a certain capacitor, the capacitance C of a certain capacitor is constant. So for a parallel plate capacitor, the capacitance is given by this equation. So this is an example of a parallel plate capacitor. There are two plates separated by a dielectric. So this is the equation or expression of a parallel plate capacitor. As you can see, there is no Q or V in the equation. There is the permittivity of the dielectric material, there is the cross-sectional area of the metal plates, and the distance between the metal plates. So there is no Q charge or V voltage in this equation. So the capacitance depends on the physical dimension of the capacitor instead of the voltage or charge. So A is the surface area of each plate, D is the distance between the plate, and epsilon is the permittivity of the dielectric material between the plates. So even though this equation is only valid for parallel plate capacitor, and there are different types of capacitors, such as cylindrical capacitors, capacitors of other shapes, but the relationships more or less remains the same. So we may infer from the equations of parallel from the equation of parallel plate capacitor is that in general there are three factors that determine the value of the capacitance. The surface area of the plates, A here, the larger the area, the higher the capacitance is. And the spacing between the metal plates, so the closer the metal plates are, the higher the capacitance is. And the permittivity of the material is also another factor that affects capacitance. The higher the permittivity is, the greater the capacitance is. So C is equal to epsilon A divided by D. So here are some of the symbols and examples of the capacitor. So this is a fixed capacitor and this is a variable capacitor. And capacitors are often named based on the dielectric material. So if the dielectric is polyester, you have polyester capacitor. Dielectric could be ceramic, dielectric could be glass. So dielectric is a material that is not a good conductor of electricity and that has very high resistance. Okay, we know Q is equals to CV. If we differentiate this equation with respect to time, we end up with the equation of current through a capacitor. So we know I is equals to dq dt. So if we differentiate this, we end up with I is equals to C dv dt. So that's the voltage current relationship between a capacitor. Now let's compare it with resistor. What is the voltage current relationship of a linear resistor? V is equals to IR. A linear resistor obeys Ohm's law. But capacitor is not a linear circuit element. Capacitor does not obey Ohm's law. So the voltage current relationship V equals to IR does not apply for capacitors or inductors. It only applies for resistors. And the voltage current relationship between capacitors is I is equals to C dv dt. So if we plot I versus dv dt, we end up with a straight line that goes to the origin. And if we take the slope of this curve, we end up with the capacitance. Capacitors that satisfy the above equation are said to be linear. For a nonlinear capacitor, I versus dv dt will not be a straight line. It will be a curve or something like that. So although some capacitors are nonlinear, most capacitors are linear, and we'll assume linear capacitors in this course. Okay, so if we know the voltage, equation of voltage of a capacitor and capacitance, we can determine the current through the capacitor using I equals to C dv dt. But what if we know the capacitance and the current? How then we determine the voltage? So if we integrate this equation with respect to time, we end up with the voltage equation. V is equals to 1 by C integral I dt plus initial condition. So Vt naught here is the voltage across the capacitor at time t naught. So Vt naught here is basically indicates the initial voltage of the capacitor. So here we're beginning our observation at t naught, and we want to know the voltage at time t. So that's why we need to consider the initial voltage due to the initial charges stored in the capacitor into our equation. So the above equation shows that the capacitor voltage depends on the past history of the capacitor current. So the capacitor has a memory, a property that is often exploited in digital circuit design. So the voltage doesn't only depend on time t, it depends on from t naught to t, which is an earlier time. So in order to determine voltage at time t, we need to know the current from t naught to t. So it depends on the past history of the capacitor current. Okay, so we know P is equals to VI. From this we can determine the voltage, the power relationship of the capacitor. So if we were put in this equation I equals to V dv dt, I equals to C dv dt, we end up with the power equation. So this is the equation of instantaneous power of a capacitor. Now, we know W is equal to integral P dt, so if we integrate power with respect to time, we end up with the energy stored in the capacitor, and if we perform the integration, we end up with something like this: half CV square, and the upper limit is V of minus infinity, and the lower limit is V of minus infinity, and the upper limit is V of t. So what does minus infinity here mean? Minus infinity here means at a time when the capacitor was totally uncharged. So when the capacitor was totally uncharged, Q is equals to 0, the voltage also has to be 0, because we know Q is equals to CV. So if Q is equals to 0, capacitance cannot be 0. That means voltage has to be 0. So the capacitor was uncharged at t equals to infinity. That's something we always assume. So if we put that in the limit of integration, we end up with the equation of the energy stored in a capacitor. W is equals to CV squared by 2, where C is the capacitance of the capacitor and V is the voltage of across the capacitor. So if we apply Q equals to CV in this equation, we get an alternative expression of energy, W equals to Q squared by 2C. But you don't have to memorize that. You just need to learn this one. Energy is equals to CV squared by 2, and Q equals to CV. And of course, I equals to C divided T. Okay, so we're now going to analyze the equation I equals to C divided T and determine some important corollaries from that equation. So the first one is that if voltage is constant in this equation, differentiating a constant is, we get 0, which means the current is also 0. So when we discussed open circuit and short circuit in an earlier lecture, we discussed that if the current through an element is 0, we can replace that element with an open circuit. And if the voltage across an element is 0, we can replace that element with a short circuit. In other words, since the current is 0 here, the capacitor can be replaced with an open circuit. So a capacitor is an open circuit to DC. Constant voltage means DC. So a capacitor is an open circuit to DC. Another important point or property of capacitor that we can derive from this equation is that the voltage of a capacitor cannot change abruptly. So how do we know that? So let's say, for instance, in figure A here, the capacitor voltage here is changing up to this. So this change is not abrupt. So it takes a particular period of time, here to here, let's say 10 seconds, to complete these changes. So this is allowed. But what is not allowed is the change in figure B here. At t equals to 0, the voltage abruptly rises from 0 to 1, or 0 to some voltage. And this change is also not permissible. At some other time, the voltage abruptly drops from some level to 0. Why is it not permitted? And how can we relate this to this equation? So for this equation, at t equals to 0, there is the delta V, or dV, has a certain value, let's say 10 volts, for delta t equals to 0. So I equals to C dV can also be written as C del V divided by del T. So del V here, or dV here, has a certain value, let's say 10 volt, but del T here is 0, because it's instantaneously jumping from 0 to 10, which means the change is instantaneous, which means the delta t, the time that is required for this jump, is 0, and something divided by 0 is infinity, which means the current is infinity, which is not possible. Therefore, the voltage on a capacitor cannot change abruptly. So this continuous change in voltage requires an infinite current, which is physically impossible. So the capacitor resists an abrupt change in the voltage across it. Another important property of a capacitor is that in this course we'll assume ideal capacitors, which does not dissipate energy. It only takes power from the circuit when storing energy in its electric field and returns previously stored energy when delivering power to the circuit. So it does not dissipate energy or convert energy to heat or light, just like resistors do. But a real non-ideal capacitor has a parallel model leakage resistance. So this leakage resistance can be really high, like 100 mega ohms, and therefore can be neglected. So for this reason, if we assume ideal capacitor, it does not create a great margin of error. So the margin of error for ideal capacitor is acceptable. But know that a real capacitor is modeled with the capacitance in parallel with the leakage resistance, and the leakage resistance is extremely high. So here is a problem to test your knowledge. So please pause this video and try to solve the problem, and then we'll match our answers. So hopefully you've been able to solve this. Here C is given, V is given, Q is equals to CV, and the energy stored is CV squared by 2. Here is another problem. Please pause this video and try to solve this problem. So hopefully you've been able to solve this. V is given, C is given. We know the current I is equals to C divided T. If we differentiate with respect to time, we obtain the equation of current. So here is another one. Please pause this video and then we'll match our answers. So hopefully you've been able to solve this. Here the current is given, the capacitance is given, the voltage is required. So V is equals to 1 by C integral I dt. And the initial capacitor voltage is 0, which means V0 is 0. Here the initial voltage is 0. And that is our final voltage equation. So here's another problem. Please pause this video and try to solve this problem, and then we'll match our answers. So please pause. So hopefully you've been able to solve this. So the voltage equation here is given, the capacitance is given. We know I is equals to C divided D, but there is no easy way to differentiate a graph. So here we convert this graph into an equation, and then we can determine the current. So this is a piecewise linear curve, which means it's composed of several straight lines. One that exists from 0 to 1, another that exists from 1 to 3, and the third one exists from 3 to 4. So the first straight line that exists from 0 to 1 goes from 0, 0, and 150, so we can determine its equation. And then if we differentiate it with respect to time, we get the current. Similarly, we do the exact same thing for the straight line that exists between 1 to 3 seconds and the 3 to 4 seconds. So we have two more equations. If we differentiate them with respect to time, we end up with the current. And if we plot this, this is the final output. So here's another problem. Please pause this video and try to solve this problem, and then we'll match our answers. So hopefully we've been able to solve this problem. So the question clearly states under DC conditions, which means we can replace the capacitor with an open circuit, because the capacitor is an open circuit under DC conditions. And this one, we can also replace it with an open circuit. Even if it wasn't mentioned in the question, we can still see that it's a DC circuit, because the only source here is a constant current source. It's not something like 6 sine omega t or something. So it's a DC circuit, and for DC circuit we can replace the capacitor with open circuits, and then we have this reduced circuit, and then we can apply just Ohm's law or voltage divider, current divider, to determine the required voltages and currents. And lastly, we apply energy is equals to CV squared by 2 to determine the energies of the two capacitors. So we'll continue our discussion in the next capacitor lecture. So thank you.